Okay, good afternoon. Our speaker today is Lukas Merten. He's now a lecturer at the University of Bochum in theoretical physics. He also got the master there and then the PhD working on mainly, I guess, galactic cosmic rays and try to model their propagation. He also did a postdoc at the University of Innsbruck. He is one of the developers of the CRPropa code, which is a very famous one to track the propagation of cosmic rays across the universe from extragalactic to galactic scales. He's also a member of IceCube, among other things. And today will tell us a bit more about this fascinating topic. Please.
Yeah, thanks for the kind introduction. And to you, it's going to be a little bit more interactive than you probably expected. So I hope you had lunch and already a coffee afterwards. Because at some points, but I will let you know where you have to do something. So usually that is a topic where I give a whole lecture series on, so I had to cut it down significantly, but I couldn't make all the choices. So that's where your interaction is needed to help you pick the right topics that are interesting for you. I hope that works out. I never tried it before. So I also value your feedback afterwards. All right, so what I prepared is a short introduction on cosmic ray interactions and transport, and why I think that this is something important that we should look into. Then I prepared basically three different approaches to model that, which is single particle simulations, ensemble average transport, and nonlinear energy spectra evolution. There you can pick one or two topics depending on how fast I am. Then I prepared a couple of examples, also way more than what we can take a look into. That's the second part where you have to make a choice, and then short summary and outlook. In general, whenever you have any questions, just let me know in between or just ask afterwards. So let's start with a few observations. Basically, we know three things about cosmic rays. The thing that is best measured since more than 100 years is the energy spectrum of cosmic rays. And we do see that spans over something like almost 30 decades in flux. So that's what's on the y-axis, and something like 14 orders in magnitude in energy. And if you don't plot it in a weighted way, but like here, I mean, it's hard to see any features by eyes. It looks like almost a perfect power law, which is quite interesting because we are now pretty sure that those cosmic rays can't come all from the same kind of sources, but must come from different source classes and from inside the galaxy and also from extragalactic sources. So they seem to have something in common that produces a power law, and transport seems to not really change these underlying features of the energy spectrum. The second thing we know about the cosmic rays is their chemical composition, here shown in different mass groups. So again, the cosmic ray flux, but now weighted with the energy to the power of 2.7 to make these kinks and features more visible. And the take-home message here is we do see that the flux is changing over energy, and the composition is also changing. That's the key take-home. All the details, we can talk about that afterwards, but yeah, the take-home is something is happening depending on the energy to the cosmic rays during likely propagation that changes their chemical composition depending on energy. And the last observable that we have is arrival direction. So we can see from which direction the cosmic rays were coming to us. Here exemplarily shown the dipole amplitude in the upper panel and the dipole direction in the lower panel. And again, we see some energy dependence. And if you're brave enough, you could say down at the lowest energies, we might see something that is proportional to e to the power of 1/3, which we would expect from pure isotropic diffusion. But yeah, for sure, it's at least changing over energy again. So that is more or less all we know. And then we can ask ourselves the question, why do we need the modeling of cosmic ray transport? And That is because cosmic rays are deflected in magnetic fields, and that is a pretty nice sketch from a colleague, Patrick Reichertzer, who made that sketch and shows us how cosmic rays propagate in magnetic fields. So magnetic fields are these blue ribbons, and the cosmic ray trajectory is this red ribbon, basically. And we do see that depending on the magnetic field setup, like how strong the field is compared to particle energy, we do have different propagation regimes, and we don't have to go through all the equations. But what you should keep in mind is that it is important, or particles behave differently when they're propagating through magnetic fields, depending on the local magnetic field structure and the particle energy. So the magnetic fields can be structured on large scale, so with some common direction and ordering, and they can have the strengths can be also structured, for example, bound to the local density of the mass in the universe. And it can also have a turbulent component where the power spectrum, so how the energy is distributed in K-space, is described, and it can have anisotropies and something like intermittency and so on and so forth. So there are a lot of things that describe the magnetic field where we observationally almost know nothing about that, which makes it, of course, hard to describe the transport of cosmic rays in a fully deterministic way. So overall, that gives you some random deflection, which smears out sources, so they become larger in the sky as they would be if they would be true point sources. And we can also have coherent deflections, which would shift the source position, the apparent source position in the sky. That means if we look in that direction and see cosmic rays coming from there, the source could be somewhere else in the sky. And that is why we need to model the transport of cosmic rays to really link our observational direction with possible source catalogs. Yes, so that is how the magnetic field could look like. That is some simulation of the galactic magnetic field. You see that it has some structures and some voids, and then depending on where your source would be, you see either a lot of deflection or almost none. Pretty picture of the coherent component of the galactic magnetic field. So also that, even in our own galaxy, we don't really understand the magnetic field, but what we do understand is it's probably pretty complicated and makes modeling not really easy. All right, why do we need to model cosmic ray interactions? Yeah, that's simply because cosmic rays not only are deflected on their way from the source to Earth, but they also undergo a lot of interactions, and that can be interactions with ambient photon fields, like the cosmic microwave background in the case of ultra-high energy cosmic rays, or the extragalactic background light. But it can also be photon fields already in the source. So if you think about an AGN, which has some strong synchrotron fields, for example, that could serve as targets for the cosmic rays that are also accelerated in the jets. But it could also be, for galactic cosmic rays, something like the intergalactic, the interstellar medium. So just gas clouds somewhere in the way between the source and the Earth. And all those interactions need to be understood because they do change the composition of cosmic rays. So if we start only with some composition of primary particles that will go undergo interactions, and we will produce, for example, lithium, beryllium, and so on and so forth, elements that are almost non-abundant in sources. So, for example, in our own sun, and we do see them way more in cosmic rays. So they have to be produced somewhere on the way between source and observer. All right, so cosmic rays never really propagate in a pure vacuum, so we have to take into account energy losses and production of secondaries. That is a non-complete list of possible interactions from synchrotron radiation to spallation nuclear decay. double, triple, pair production, whatever you can think of, everything is happening for cosmic rays. And if you want to have a complete full picture, you want to take all of them into account, which of course is rather challenging to do. Possible targets are of course photon fields, as I said, CMB, EBL, synchrotron photons, corona, whatever you think of is producing photons in the universe is probably also at some point a relevant target for cosmic rays. We also have hadronic targets like these dust clouds and H1, H2 regions and so on and so forth. And of course, the magnetic fields. So why should we care about secondaries? First of all, I call secondaries everything that is produced during cosmic ray transport. So that can be photons, neutrinos, electrons, whatever other leptons, lighter cosmic rays, and so on and so forth. They can have quite complicated energy spectra and induce interactions again themselves, so that we have third or fourth or whatever generation of secondary particles. But they also provide a good knowledge that is otherwise inaccessible to us, because, for example, if we look at neutrinos, they directly point back to their sources. So if we observe neutrinos, and we are lucky that it wasn't just a cascade event where the point spread function is like that, we might get a good idea where at least cosmic rays have been at some point during their propagation. They also help us to understand transport properties. For example, we look at the ratio between secondary and primary particles, that is this famous boron over carbon ratio, or help us to learn about the composition if we look at muons, how they arrive on ground here at Earth. So how is that cosmic ray propagation now modeled? You saw we should take into account the whole bunch of different physics, from particle physics to plasma physics to whatever. And I would say at the moment we are not able to describe that in a single framework. And that's simply too complicated, and I mean that is also a non-complete list of things that you should take into account when you pick your framework for your simulations. We don't have to go through that. If you ever want to do some cosmic ray modeling on yourself, maybe start with a list of questions like that, and then see which framework answers your question best, and then pick that. And how does it look like, or how could you pick those or this framework? I tried to come up with a family tree of propagation tools, and you could start on the left and then go step by step and ask yourself the question: do I have stationary fields, or do I have fields that are varying in time or even nonlinear? And then walk yourself basically through that decision tree, and then come up in the end with some possible tools to use. If you do cosmic ray transport, I probably forgot your favorite one. So let me know if it's missing. I try to update that after each talk. So today, and that's where your action is now required later, I prepared more information on basically three topics. One of them would be the equation of motion solver with CRPropa, so the uppermost one, which would be single particle propagation for ultra high energy cosmic rays. Then I prepared something on the transport equation, so ensemble average transport based on stochastic differential equations with CRPropa. And lastly, I prepared something on the relatively new code, CR-ENTREES, which is a matrix solver to solve the nonlinear energy transport equation. So the question is now, which of the three topics you would like to pick? And I think we just tried out who wants to hear something about the first. So there will be 1, 2, 3, 4, 5, maybe. Okay. Second one. Okay, roughly 10, 12, maybe something. Okay, third one. 2. Okay, then I would say we start with the second one. Which is nice because we anyway have to do the introduction for CRPropa because most of that is implemented in CRPropa. So also the people that wanted to hear something on the ultra high energy cosmic ray part, don't fall asleep. That is also interesting for you. So CRPropa is a cosmic ray propagation framework that is a Monte Carlo simulation framework. That means we model individual cosmic rays or phase space elements where individual cosmic rays are used for ultra high energy extragalactic transport, and the phase space element approach is used for galactic transport, or if you want to model diffusive shock acceleration or in-source propagation. It includes many of the relevant interactions, especially on ultra high energy cosmic ray transport. For the lower energy part, we are currently working on extending that, and it's open source and modular structure. So that means you can download it, the source code is open, and if something is missing that you need for your simulations, you can more or less easily write your own modules and extend the software so it fits, in the end, hopefully your needs. It's also a community-driven project, and since I'm involved in that since a couple of years, I always like to emphasize that we have contributions from basically all over Europe and even some contributions from out of Europe. It's mainly written in C++, but it has some convenient Python steering, so it's really not too complicated to use it. It usually works on a laptop, but scales up to really supercomputing clusters with whatever 10,000 cores you want to use. And as I said, it's relatively easy to customize and extend. The central idea is that you have the cosmic ray candidate, which is a structure that holds all the information on your cosmic ray or your phase space element, like its location, its energy, its type, whatever. And then we have a selection of modules that acts on that candidate until some boundary condition is hit, and then some results are written to output file that you then later still have to post-process to get something meaningful out, like cosmic ray flux, density distributions, whatever you are interested in. The software you can look at more or less like a big toolbox where you can pick some of the tools or building blocks of your simulation, put that in a script, and then have your custom CRPropa simulation. So there's nothing like the one CRPropa simulation that you run and get some output, but you build your CRPropa simulation, and that will be different, likely from any other CRPropa simulation that was around before. So you should really see it not as one tool, but really a selection of tools that helps you to solve your problems. How does it look like? More or less like that. That is a little bit older example that runs under CRPropa 3, but the idea is still the same, also with the latest version, that you define, for example, in this case, some magnetic field. It's a turbulent magnetic field with some properties. In this case, it's a Kolmogorov turbulent field that is isotropic. You define the propagation algorithm that you want to choose. You define the interactions that you want to take into account. In this case, photopion production, photodisintegration, electron pair production. So that is beta-hydra pair production and nuclear decay. You declare a boundary condition and some administrative stuff, so which output format you want to like. You prepare a candidate, so your cosmic ray, and you run the simulation. And that's what the results would look like. You have a cosmic ray that is deflected in turbulent magnetic field, and then it's producing, during the propagation, more and more secondary particles that are deflected in different direction because the field is just turbulent. And from that, you could, for example, learn what kind of spread you would expect from a point source that is away in a turbulent field. And of course, it makes a nice picture. All right, so that was the general introduction, and now we skip the part on the ultra high energy cosmic rays and go to the high energy cosmic rays in the ensemble averaged approach. So in general, those cosmic rays have gyro radii that are so small that we are no longer interested in them. So we can average over the gyro radius, which reduces the dimensionality of our problem. And the particles would usually have some common transport feature. So we are not interested in individual particle trajectories, but only interested in the average properties of the total ensemble. We have in general much more data than for the ultra-high cosmic rays, so which makes comparison a bit better. But on the other hand, we have small gyro radii, which is good on the one hand, but on the other hand, we have to take into account all the turbulent magnetic field structures. We have a relatively high energy density, which means that in principle, we might need to take into account some nonlinear feedback of the cosmic rays on their surroundings. And that is usually happening in denser environments. So we have dense photon fields or dense matter fields. So we have many different interactions to take into account. How do we do that? Usually with a transport equation that looks like that, which is in this case, it's the Fokker-Planck transport equation. It's the basically it describes the time evolution of. Now I would grab my mouse somewhere. Yes. So we have the time evolution of the particle density n, and we do have some diffusion terms here, some drift terms here and there, which would be advection of the particles. And then we have adiabatic energy changes, second order Fermi acceleration, or momentum diffusion, and some lost terms and sources, whatever. This equation can be rewritten to something like that, which is just some algebra. But the nice thing is, from that equation, we know how to transform it into a set of stochastic differential equations via Ito's lemma. And if that all was too quick, it doesn't matter. We can discuss about that afterwards. The interesting part is we can solve these stochastic differential equations. So this equation down here that has some deterministic part and some stochastic part, where this is a Wiener process for those of you who are interested in. The interesting part is we can solve that equation numerically pretty similar to a normal equation of motion. And that means we can basically use the same techniques as we use for the ultra-high cosmic rays, also for the phase space elements. And that means we can use all the nice framework that CRPropa provides on ultra-high cosmic rays and on the diffusive approach. We have to interpret the results, of course, differently, but the numerical techniques are quite similar. So in summary, we can use a rather simple algorithm to solve that stochastic differential equation, which is much simpler to solve than solving a discretized version of the Parker transport equation. We need no transformations of the magnetic fields, which is interesting for the user because he can do diffusion in whatever magnetic field setup he likes to do. And it works in rather complex magnetic fields like this one. Okay, so that was on the technical point of view. We skip over the energy transport, which is really interesting. And it's a pity that you didn't pick that. But if you're interested, let me know. And I mean, for sure that list is messed up. That's the first point. But I think I would like to use the last few minutes to show you one of the examples. So either you can pick 1, 2, or 3. What are you interested in? Ultra-high cosmic rays from the radio galaxy, transport in the Milky Way, galactic wind termination shock, diffusive shock acceleration, time evolution. Just whoever shouts first gets his shot.
Milky Way.
Milky Way. Good. Transport in the Milky Way. Nice topic. So the questions that we ask ourselves in that project were, does the source distribution or the magnetic field morphology have a larger influence on the particle density in the Milky Way? And how is the diffusion ratio, so the ratio between perpendicular and parallel diffusion, influencing the escape times? And for that, we did a setup where we tested 3 different source distributions. So a distribution that is following the pulsar distribution, one that is following this model of the supernova remnant distribution, and a homogeneous cylinder. And we used the general magnetic field that you saw in these pretty plots as our background magnetic field. Injected particles in a burst-like injection, so delta injection in time, let them propagate and see how the particle density evolves over time. And yes, so some explanation of the magnetic field, not really super interesting. Settings of the diffusion coefficient, we use the normal galactic diffusion coefficient that is fitted to boron over carbon ratios with a Kolmogorov isotropic diffusion. And we tested different diffusion ratios for that epsilon 10 to the -3 means almost only parallel transport. Epsilon equals to 1 is more or less isotropic diffusion. And then that should be a video. Yes. So you see face on and edge on views of the galaxy or the cosmic ray density in the galaxy. And we do see that the halo is forming after a couple of 10 million years. It's filled with cosmic rays. And we do see, if we look precisely, that we see that X shape of the magnetic field, which is one of the features of that Jensen-Farrar galactic magnetic field model. We do see some anisotropies in northern and southern hemisphere that also come from the magnetic field model. And we do see that in the spiral arms, cosmic rays stay longer than they do in the interarm regions, which is mainly because the magnetic field is more aligned in the galactic plane in these regions. And cosmic rays are just escaping less efficiently in the arms than between. From simulations like that, you can try to build stationary solutions of the cosmic ray density. And the main take-home message is that the diffusion model has really a strong influence on the morphology of the cosmic ray particle distribution in the galaxy, especially if you differentiation between only parallel and isotropic transport. So isotropic transport washes out mainly everything from structure of the magnetic field and source distribution. But if you have a strong parallel transport, the magnetic field morphology plays a crucial role in the distribution of cosmic rays in the galaxy. All right, that is basically summarized here. You can also check on the escape times. Escape times depend on the energy, as you would expect. And we found some dependency also on the diffusion ratio, which strongly, of course, depends on the magnetic field model that you put in. And with that, I would come to my final summary and conclusion slide, which is probably easier if I. No, it's stuck. Sorry. Where's my mouse? Okay. All right. So summary, better observational data challenge now our transport model, especially for the lower energies in the galaxy. We have now so much data, especially at the lowest energies, for example, from AMS, we really have energy or isotope resolved energy spectra that is really necessary to do more than one-dimensional transport equations to explain everything that we nowadays see in the data. One of the most important things that I want you to take home is that there is not the simulation framework for cosmic ray transport. So whenever anybody says, I have the solution to do it in one single framework, I would strongly doubt it. And it's important to pick the right framework for the problem that you really have at hand. Although the modeling is complicated and comes with a lot of unknown things like the magnetic field structure, cross sections, and so on, there's still a lot that we can learn from modeling that would be otherwise inaccessible to us. On the outlook point of view, I think in the next years we will hopefully at some point be able to connect galactic and extragalactic cosmic ray models, which is harder than one might think. If you know why, discuss with me later. And that we get consistent description of ballistic and diffusive transport, because nowadays we have frameworks that can do diffusive transport, and we have frameworks that can do the ballistic transport, but we have not a framework that can do basically switching consistently between the two approaches, which would be necessary to describe the transition between galactic and extragalactic cosmic rays in a really nice and consistent way. And what I didn't speak of, because that was in that nonlinear energy transport code, is that in the future we hopefully are also able to include the description of heavy elements in the sources directly, because we do think that interactions in the source already changes the composition quite dramatically before we even start the propagation from source to Earth. That's it. Thank you for your attention.
So, questions for our speaker? Any from the PhD crowd? Wow. Let's pretend Carl made it. Yeah.
I used to be a PhD. So I was curious about the movie you were showing for the Milky Way. It looks like you have an asymmetry above and below the plane. So where does it come from? Is it the structure, the geometry of the magnetic field? Or?
Yes. So that is, I mean, that is really one of the questions that I'm always asked when there are people in the crowd that do not the modeling part, but come more from observational point of view. And that is simply because it's implemented in that magnetic field model. And I don't think that this is a feature that should be in a galactic magnetic field, because there are no real, neither from theory point of view hints on that, nor really from the observational point of view, apart from the fact that there was one fitting parameter in that model that could not be constrained. So they picked the upper limit to put it in the model. And that explains the north-south anisotropy. Yes, apart from that, it was a nice test case, that model, because it has this X-shaped structure. It is rather complicated, and we wanted the model to test our algorithm on. Therefore, we picked it. But that precise feature, I would really doubt it if it's real. By the way, it was updated like 3 days ago, that model. I didn't check it yet, but there is an update of the Jensen-Farrar model now, Unger and Farrar, which came out like 3 days ago. I hope that is fixed, among other things that are problematic with that model.
There's a question by Eleonora online.
Sì. Ciao Lucas. I'm curious about the ultra-high energy cosmic rays in radio galaxies. Can you tell us something?
So yeah, that was mainly work done by Björn Eismann in Bochum, a colleague. And for that study, we used for the first time a sample of, I think it was a couple of hundred radio galaxies, and we used for the first time a normalization in the simulation, which means that we did not simply propagate arbitrary fluxes and then fix the normalization by fitting to the observed spectra, but gave the normalization, or took the normalization from radio observations of the source and introduced weights to our cosmic rays, and treated that consistently through the simulation, and reduced with that the final normalization, which was done before, usually in all the other simulations. So which meant you would get some information on changes in energy spectrum, but you wouldn't check on, for example, total cosmic ray power constraints. And that was the new thing that we introduced there. And that it was a full 3D simulation, including analysis of the anisotropy together with composition and energy spectrum, which uses like orders in magnitude more computation power, but gives you access to that third observable, which from my point of view, since we now do have anisotropy observations, even at the highest energies, it's really something that we should take into account.
Okay, what was the result?
I mean, the result was, as many studies before, that you need a few close by, very powerful, unexceptionally bright radio sources, for example, SEN-A, something in the Fornax region, or similar, to explain the very highest energies. So really the last 2-3 data points in the Piaget energy spectrum. The bulk of the lower energy cosmic rays can be explained with a pretty normal radio galaxy distribution, but it can also be explained by starburst galaxies. It can also be explained by AGN. So the problem is really the last data points in energy, because the source needs to be close by, so that not everything is photodisintegrated when it's reaching us. So for example, if you only take a look at the radio power, something like Cygnus A would be a nice source because it's super powerful, but it's just too far away. It's at 250 megaparsec. Iron is completely photodisintegrated before it reaches us.
I think you also need a pretty strong extragalactic magnetic field to deflect stuff away from the source, otherwise it will show up as a spot.
Depends on the strength of the galactic magnetic field too. So if the galactic magnetic field has a reasonably large turbulent component, then you get a pretty good isotropy at the energies, let's say up to 10 to the 19 point something electron volts. Above that, yes, it gets problematic to get the right. I mean, you need the sources in the right position on the one hand. We do see now in the Piaget data that at least there is a dipole at, what is it, 8 eV and 32 eV, I think. So you also want to match that. But the higher order multipoles are pretty much not observed. So that makes it hard with a few individual sources to get it done. But that is, I mean, that was the main take-home message that we found. It is important to take the deflections into account, but because if you simply put one strong source in a 1D simulation, you get the energy spectrum right, you get the composition right, but then you would have one strong source lighting up somewhere in the sky, which is not seen. So yeah, I mean, in some ways, with the radio galaxies, Björn managed to find a fit that worked. But for us, the more important thing was really to show that the three-dimensional transport should be taken into account.
Okay, thank you.
Okay. No more questions, so thanks.